Good morning guys. Today we'll be looking at problem number 40 in your modeling and analysis lab. The topic is thermal analysis of 1D problem with conduction and convection along with boundary condition. The question statement is a furnace wall is made up of inside silica brick of thermal conductivity K is equal to 1.5 watt per meter Kelvin and outside magnesia brick of thermal conductivity of K is equal to 4.9 watt per meter Kelvin, each 10 centimeter thickness. The inner and outer surface are exposed to the fluid at temperature 820 degrees Celsius and 110 degrees Celsius respectively. The contact resistance is 0.001 meter square Kelvin per watt. Full stop. The heat transfer coefficient of inner and outer surface is equal to 35 watt per meter square Kelvin. Find the heat flow rate through the wall per unit area per unit time and the temperature distribution across the wall. So this is your diagram. You have this is the inner side, the left hand side, that is made up of silica brick, and outside layer is made up of magnesia. Between these two have a contact resistance of 0.001 meter square Kelvin per watt, and this side will be your inside temperature, that is where your convection occurs, that is 820 degrees Celsius, and this is your outside convection occurs, that is 110 degrees Celsius. And how these particular temperatures varies across the walls is the task, and what will be the temperature distribution across the wall is a task to find. So I will be converting every unit, that is thermal conductivity unit or heat transfer coefficient unit, all in instead of Kelvin I will be converting into degree Celsius. So this is the diagram. So this side will be your convection occur, we'll take it as T1, that is 820 degree, and this will be a thermal conductivity K is equal to K1, that is for silica, that is 1.5 watt per meter square degree Celsius, and the temperature T2 will be on the wall and temperature T3 will be the exit of that particular silica wall. Between silica wall and magnesia wall we have a contact resistance of, that is 0.001 meter square Kelvin per watt. I'll convert that into degree Celsius, and then starting of your magnesia wall will be temperature T4 and has a thermal conductivity of magnesium, that is K3 is equal to 4.9 watt per meter square per meter Kelvin, converted into degree Celsius, and the exit of that particular magnesia wall will be T5, and the where convection occurs we'll take it as T6, that is 110 degree Celsius. So this is your diagram, how you need to distinguish or convert that into element as well as node diagram, FEM model. So if you try to do the theoretical solution by HMT method, you know that heat flow through composite wall Q is equal to delta T or suffix overall divided by R. R is your thermal resistance. So Q is equal to T1 minus T infinity. So T infinity here is your temperature which is at the exit end, that is T6. So T1 minus T6. Next R, your thermal resistance is 1 divided by H1 is your thermal coefficient which occurs inside and outside temperature. So HI refers inside and A is your area which you can take it as assumed as 1. Next plus L1 is your length of your convection divided by K1 is a thermal conductivity into area plus L2 divided by K2 into A2 plus L3 divided by K3 into A3 plus 1 divided by H outside into area. In this particular equation area is common. So while you substitute it, this is your heat flow value, that is 4889.44 watts. Using this heat flow through the composite wall, I can find out what is my missing temperature, is T2, T3, T4 and T5. So you know that when you know the interference temperature Q is equal to H, that is this particular h into a in bracket t1 minus t2. You already know what is q, that is 4889.44 is equal to h inner is thermal coefficient h is 35 into area is 1, which you have assumed is 1. T1 is 820 degrees Celsius minus T2. So you get T2. Similarly, T3, T4 and T5 can be determined by HFT method. We can also use FEM method, but the process is very lengthy. Now coming to this particular answer solution, how do I do it in answers? So when you come to your answers, what you have to do is go to preference, go to thermal, click OK. Next, go to preprocessor, element type, add, again click add. In this, what you have to do is you have to go for link. One is 2D convection, click apply, then go for convection. We have both convection and as well as convection, so you need to have two types of elements. So you have two types of elements. So you have type 1 and type 2. Type 1 is link 32, that is convection, and type 2 will be your link 34, which is for convection. Now close it and go for real constant, click on add. Now type 1 link 32, click OK. Cross sectional area is 1 because already assumed as 1. Click OK. Now close it. Again click on add. Why I am adding is because we are left with type 2. What will be the cross section for your type 2 element? Click on OK. So real constant set number 2 for type 2 will be area will be again 1. Click OK. Now close it. So you have two elements, one is convection and one is convection, and also you have two real constant for convection as well as convection. So go to material props, you go to material model. Now here in material model you have thermal, double click it. So here remember your diagram. Your diagram is very important, for which you have to create your material model. So first one is you have convection. So what you have to do is convection, click on convection, double click it. So inner and outer thermal coefficient is how much? It is 35. So type 35, click OK. So first is your convection, then comes your convection. So go for material, again click on new, and now define material ID is 2, click OK. Now you go for conductivity. So while clicking your conductivity, double click it, isotropic. Now it will ask for thermal conductivity value for your first element. So first element is your silica, right? What has a thermal conductivity of 1.5. Click OK. Next, again new one. Why it is new one? Because we have a thermal contact between silica and magnesia. Again click on new model. So material ID will be 3. Click OK. So you have a new material model number 3. Now again isotropic, and 1 you have to assume it has a thermal conductivity of 1. That is your contact resistance. Next, again come for magnesium. Click on new model, material number 4. Material number 2 is for silica. Material number 3 is for contact resistance. Material number 4 is for magnesium. So click on isotropic. Now isotropic, then what will be your magnesia thermal conductivity is 4.9. Click OK. Last but not least, again what you have to do is click on new model, material number 5. Now here is outside convection. Outside convection is how much? Again 35. Inner and outer thermal coefficient is how much? Is 35. Click on OK. So you have one convection, 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 convection and convection. So you have to have 4 models. Now close it. So once you close it, now what you do is go for modeling. So modeling. Now go for nodes, model, go for create element. Sorry. Go for nodes. inactive CS. Inactive CS, what you have to do is inactive CS. So first node will be at the location of 0, 0, 0. That is x is equal to 0, y is equal to 0, z is equal to 0. Apply. Second node is at the distance of 0.001. That is your convection length. Next, third, you have the silica has 100. So 100 plus 001, that is for convection area which you already left. So apply. Next, fourth one, you have a contact resistance, again 1. So it will be 1.102. Apply. Next, fifth one, it will be plus 100, that will be 202. Apply. Now sixth one is node will be 203. So you have to have 6 nodes. So you can see here this diagram, first node here, second node, third node, fourth node, fifth node, sixth node. So you have to have 6 nodes. I already created 6 nodes. Now go for here elements. Okay, element attributes. It's very, very important. Your element attributes. Now you go for, in your element type number, you go for 2. Why element type number 2 is the starting is for convection. So you have to go for element type 2. Now what happens to its real constant? If material number remains 1, but real constant should be changed to 2. That is what we have already taken for convection. So click on OK. Now go for auto numbered through nodes. Click 1 and 2. Click OK. Okay. Once you click auto numbered 1 and 2, that is fine. Next, again go for element attributes. Now change your element type number to 1 and real constant as 1. Material is 2. Real constant is 1 and element type number is 1. So click 1. Okay. Now go to auto numbered through node. Click 2 and 3. Click. Just a minute. Number, click on 2 and 3. Okay. Next, again go for element 1, 3, and now go for element attributes. In element attributes, now material number 3, what happens to real constant is same. So after clicking 3, click on, go to auto number through nodes 3 and 4. Click OK. Next, again go for element attributes. Click on number 4. Again same thing. Now through nodes 4 and 5. So what other thing is very important is link 1, that is 1. Link 32 is for material number 2, 3 and 4. Real constant is 1. So only thing changes is for element 1 and element, that is element 1 from 1 to 2 and element from 5 to 6 changes to convection. Okay. So I go for element attributes. Now I'll change it to 2, material as 5, real constant as 2. Click OK. Go to through nodes. Click on 5 and 6. So this is how we have to create your element attributes. Once you create your element attributes, now you can go for solutions. So what you could do is go for solution analysis type. In this, you click new analysis, check whether it is in steady state condition. Click OK. Now go for define loads. So apply. So thermal. In that thermal you have temperature. Click on temperature. After clicking on temperature, what you have to do is click on nodes. So click on first node. Click OK. So it will be like this, like all the way up, and temperature. Click on temperature, type it as 820 degree. So first temperature is 820 degree. Now click on OK. Now again click on nodes. Now click on the sixth node. Click OK, and the temperature at the exit end is 110 degrees Celsius. Click OK. So temperature at node 1 is 820 and the exit end is 110 degrees Celsius. Now what you do is, now go for solution, solve current LS. So when you solve it, it says that solution is done. Close it. Now this is your solution. So now what you have to do is go for general first side. You can go for plot result, contour plot, nodal solution. In that DOF nodal solution, click on OK. Get this diagram. So you need to table it, right? So go for element table, go for define table, click add. In that you have temperature, right, by sequence number. You can name it as temperature temp, and go for by sequence number SMISE 1. Click OK and close it. Now list table, click on temp, click OK. So this is your heat flow through your composite wall, and also you can find list result of a nodal solution, the area of nodal temperature. This will be your temperature varying across each wall section, that is 820, 68, 354, 349, 249 and 110. So that is exactly matching with this. We got 680 and T2 as 680. You can always check it with this. So we got T2 as 680 and T3 as 354.03 degrees Celsius. Again same, we got 354.36 and T4 as 349 and T4 in your calculation is 349 and also T5 as 249 and here T5 also 249. So that will be your solution. Thank you.